As we have discussed, the RIJ approximation cannot really reduce the formal scaling of the couple cluster method. Cos-x can in principle reduce the formal scaling. If you use Rij cos-x maybe in tandem, they can reduce the formal scaling, but not super effective in doing big calculation. So, for doing couple cluster method, the best way is to go to local correlation approaches, and it is one of the main strength of the software package ORCA is its arsenal of local correlation approaches both for closed shell and open shell systems, as well as few multi-reference method property calculations are available. So, this is what makes an ORCA a powerful tool to perform accurate wave function based calculation. Now, what we do in local correlation approaches? So, in local correlation approaches, what we do is that we use the orbital rotation technique to reduce compress information. And so, this is how the canonical orbitals look like. These are occupied orbital in the Hartree-Fock molecular orbital theory. So, they are generally delocalized over the whole system. What you can do is that you can do an unitary transformation. So, the orbitals are localized on the particular part of the system. Now, because my correlation effect, the dynamic component of it has a short range effect. So, because of this I can actually get the orbital interaction between the two orbitals minimized by doing this unitary transformation. So, if the two orbitals are localized far away from each other, the interaction will be between them will be minimal. So, you can neglect that kind of interaction in your calculation, and that leads to what is called a local correlation approach. Now, the local correlation approaches can be divided into two categories, and because the correlation approach is 1 by r to the power 6 scaling, this is the formal scaling. So, you can actually use this one to reduce the computation cost. Now, the local correlation approaches can be divided into two categories. First is a piecewise local correlation approach. Because my interaction at the long distance are very small, so you can cut the system into small fragment, calculate their individual energies and then add them together. Advantages: the calculation on the each fragment can be done independent of each other. So, it can lead to a massively parallel implementation, which sometimes are called embarrassingly parallel. I do not understand what is embarrassing about it, but it can lead to a massively parallel implementation. Problem is that kind of systems you do not get a clean definition of the total wave function, or how to go beyond ground state energies. So, this kind of local correlation, fragment based local correlation approximations are very good for ground state. You cannot have a clean definition of the property, or it is very difficult to extend it to the excited state. On the other hand, you can have the direct local correlation approaches where you do not fragment the molecule, you keep the molecule as it is, but depending upon what kind of interactions are important, you drop away certain term from the Hamiltonian. So, your calculation is still on the entire system, but because you are only correlating a part of it, your computation cost got reduced. These are much less parallelizable than the piecewise local correlation approaches. The advantage is that you have a clean definition of the wave function. So, you can actually do property calculation with this method, you can extend them to excited state, and that is why in the recent times the local correlation based approaches has become most popular. Now, this is about the occupied orbital, what you do to the virtual orbital. Now, the canonical virtual orbitals are a chaotic space, because whatever was bad in my occupied orbital during the variational optimization, remember in the Hartree-Fock only the occupied orbitals are variationally optimized. So, what happens is that whatever was bad in the occupied orbital, they get translated to the virtual orbital during the optimization process. So, the virtual orbitals are very chaotic and they are completely delocalized. You can in principle try to do some kind of a localization, but they are not often very good. So, you cannot use localized orbital for the virtual orbital. What you need to use is called the natural orbitals, and they are obtained by diagonalizing a correlated density matrix. The recipe is given by Loudin's 1955 paper. So, my Hartree-Fock orbitals are generated by diagonalizing a one particle reduced density matrix or the charge density bond order matrix, and they have an occupation of either 1 and 0. Whereas, if you diagonalize a correlated one particle reduced density matrix, you will get so called natural orbitals where the occupancy is between 1 and 0. For the case of the Hartree-Fock, it was either 1 or 0, but here is something between 1 and 0. So, natural orbitals can be considered as a one particle representation of a multi-determinant wave function. Hartree-Fock the orbitals are one particle representation of a single determinant, and because it's a one particle representation of a multiple determinant, they are more natural to the exact wave function. That's why they are called natural orbitals. And Loudon has shown that the electronic structure calculation converges very quickly with respect to the orbital size if you use natural orbitals. Virtual orbitals, if you use canonical virtual orbitals, generally your calculation converges very slowly with respect to the size of the virtual space. Problem is that to get the natural orbitals, you need to solve the electron correlation method. So, this leads to you an egg first or a chicken first problem, because you want the natural orbital to solve the correlation problem easily, whereas to get the natural orbital you need to solve the correlation problem first. But the good thing is that you can use what is called an approximate natural orbital. So, a natural orbital generated from an low cost approximated method like MP2 can be used to reduce the orbital space for a much higher level correlation method like CI or couple cluster, and that is what make the natural orbital a so attractive schemes. So, that means we are going to not use exact natural orbitals, we are going to use approximate natural orbitals. Now, among the various kind of natural orbital used, which we are going to use what is called a pair natural orbital. So, that means I will generate a natural orbital for each electron pair. The advantage is that my natural orbitals are mostly localized over the same space as my occupied orbital. Their occupation numbers falls very quickly. So, only a few number of natural orbital has to be considered for each pair. Problem is that because now I am generating the natural orbitals separately for each pair, they are not orthogonal to each other. So, I have to deal with this non-orthogonality, but if I can handle this non-orthogonality, my orbitals, my size of my virtual space in terms of natural orbitals are very localized and they are very small. So, this is what is used using a pair natural orbital. Now, what I do using this localized occupied and pair natural orbitals, I actually rewrite my couple cluster as a pair correlation problem, and I have different electron pair. Of course, the orbitals which are localized on the electrons which are localized on orbitals which are close to each other, they will have more interaction and more contribution to the total couple cluster energy, because I am rewriting the couple cluster as a pair correlation energy. So, total couple cluster energy is sum of the pair correlation energy of all the pairs. Now, the orbitals which are close will have more contribution to the pair correlation energy. The orbitals which are far away will have a negligible contribution of the energy, and using this one I can actually reorder my set of electron pairs into increasing order of contribution, and the pairs which makes a negligible contribution to the total energy, I can treat them in an approximate method like MP2, whereas the pairs which makes a high contribution to the total energy, I treat them in a high level couple cluster method, of course in a truncated space generated by the PNOs. That means I want to treat each pair fairly, but being fair does not mean being equal. Second thing is that because in this treatment I am truncating on the base of energy, not in the base of any geometrical criteria, distance or anything, there is no real space criteria. So, these methods generally give very smooth potential energy surfaces, which is a problem with the methods which uses a geometric based criteria, because energy may not always strictly follow the geometric dependence. So, this is a good approximation. So, by using this kind of approximation, what you can do couple cluster calculation on an entire protein crumbing. This is in 2013 paper, this calculation was done, and this is almost impossible to do with any standard untruncated unapproximated couple cluster method. So, this is computational chemistry as its best. So, the ORCA, the most powerful set of local pair natural orbitals based couple cluster available is called DLPNO-CCSD. So, this DLPNO-CCSD gives you gold standard result, maybe at the cost of iron. Why I say iron? Because iron is cheap, at the same time so important mineral. You could have used some other acronym for it. The advantage is that means what I want to say is that it can give you energy which is very close to CCSD parenthesis T, which is considered as the gold standard of the quantum chemistry, at a very less expensive cost. So, that means I can now do calculation using DLPNO-CCSD on a large system for which you cannot do a normal couple cluster calculation. Why the name DLPNO come from? This uses domain based pair natural orbitals, not only pair natural orbital but domain based pair natural orbital, that is why it is called DLPNO. Although I am saying that you can actually do this calculation, but this method actually has a huge memory and storage requirement. When I say huge, if I am comparing to Hartree-Fock, although you can do computation cost of DLPNO-CCSD-T for large system is generally 2 or 3 times more than the Hartree-Fock, but the memory requirement or the storage requirement for doing these calculations are generally huge. So, if you want to do a DLPNO-CCSD-T calculation for any practical system, you need to make sure that the machine you are using has sufficient amount of free hard disk space and sufficient amount of RAM, preferably something more than 16 GB to do this kind of calculation, and you should not try doing this calculation on a very large system. The CH2 molecule may be still fine, but I will not try to do a DLPNO-CCSD-T calculation on my laptop if my system size is more than 10 light elements. So, how the algorithm actually works? So, I first solve the Hartree-Fock. After that, I localize the occupied orbitals, and the accuracy of this DLPNO-CCSD-T method is described by various truncation thresholds, and there are basically 4 thresholds which generally dictates its accuracy. So, and for the each step involved, I will mention the corresponding threshold. So, I will first solve the Hartree-Fock, I will localize the occupied orbital, and I will choose the electron pair which has to be treated at MP2 level and which has to be treated at couple cluster level. The corresponding keyword is T-cut pair. Then I will localize the virtual orbitals in terms of projected atomic orbitals, and I will construct the correlation domain. So, the T-cut DO will give me the threshold for describing this correlation domain, and of course, to generate all the integrals over localized occupied or projected virtual orbitals, I will use the density fitting approximation. So, correlation domains will not only be considered for orbital basis set, but as well as for the auxiliary basis set also. So, the T-cut DO define the threshold for the orbital basis set, and T-cut MKN define the threshold for the auxiliary basis set for the density fitting. Now, in the next step, my virtual space, which was now expanded in projected atomic orbitals using correlation domain, now I will truncate is using PNOs or pair natural orbital, and the corresponding threshold is given as T-cut PNOs. So, these 4 cutoff criteria together determine the accuracy of the DLPNO-CCSD-T method. Now, there are preset criteria available in Orca, so you do not have to really play with all these criteria. And once you do the truncation and generate all the integrals in the PNO basis, then you solve the CCSD-T equations in the PNO basis using a localized occupied orbital. Now, this threshold, as I was saying, that these thresholds are predefined in Orca, and there are 3 thresholds actually: loose PNO, normal PNO and tight PNO, which gives you the higher accuracy at the expense of more computational cost. So, generally the increase in the computational time is roughly 3 times when I go from loose PNO to normal PNO, and 3 times again from normal PNO to tight PNO. So, generally if I go to loose PNO, tight PNO, it is 9 times more computation costly. This I am talking in a very rough sense. It depends upon what kind of molecule you are using, what kind of machines you have. So, you can see the criteria, the truncation thresholds are actually becoming stricter and stricter as I go from loose, normal, tight, all the 3 thresholds. And the advantage is that this is 2 times, somehow the multiplicative sign is missed here. So, it is 2 times 10 to the power minus 2, 5 times 10 to the power minus 3, 3.3 times 10 to the power minus 7, 1 times 10 to the power 7, like this. So, the multiplicative sign is missing. So, loose PNOs are generally good for quick estimation, normal PNO is good for reaction energy, and tight PNO is generally good for non-covalent interaction. And if you have a case where the correlation is very strong, my starting Hartree-Fock orbitals are not good, in that case you should use tight PNO. In principle, if you put all the 4 threshold criteria to 0, that means you make it infinitely tight, you should get the canonical couple cluster energies unapproximatedly. But that's a bad way of solving the canonical couple cluster method. You should use the normal PNO or the tight PNO wherever possible, and it has the similar basis set dependency of the couple cluster. So, you need a really big basis set to get convergence with respect to the basis set size and to get good agreement with the experimental result. Now, let us go back to the example of CH2 we were looking at. and maybe see, can I reproduce the canonical result. When I say canonical result, I mean say unapproximated result. Using DLPNO methodologies. Now, so let me try to make my input file. So let me save as ch2 sdlpno .inp. So in place of RIMP2 I write and you have to write the setting for the PNO, that is I am going to use normal PNO. Showing the error. Let us see what is the error. Yeah, the spelling mistake. So it has to be normal PNO. Now we can do the calculation. So this DLPNO based methodologies are also available for MP2. So you can actually do an MP2. You can actually do an MP2 calculation with the DLPNO. The similar loose, normal, and tight PNO thresholds are available. But the thing is that the RI approximation generally gives you a very good speed up. So for most of the cases, it's sufficient to use the RI approximation for MP2. You do not really need to go to the DLPNO methodologies. Whereas for couple cluster, the advantage of using DLPNO is quite significant. So for most of the couple cluster calculation, it's advisable to do the DLPNO methodologies. Now let me try to do the triplet, make the input file and do the calculation for the triplet. Couple cluster calculation, remember, it takes some time, a lot of time. Let me save as ch2 DLPNO. DLPNO. As we are using the auxiliary basis, the RI approximation to generate the integrals, so you have to always give the /c basis set even while doing the DLPNO calculation. okay, we have saved it as a text file. I should have saved it as an input file. So, the triplet calculations are going on. Let me open the singlet output file and maybe we will try to look at the output file a little bit. So, this is where my Hartree-Fock calculation is done. After this, first my orbitals are localized, that is where my occupied orbitals are localized. And this is where I am generating my guess, and these are the different thresholds. This is where the PAOs are generated. Then I go to PNO, it says that how many electron pairs are there, and you see the number of PNOs for each pairs are very small, and there it does the couple cluster calculation and CCSD parenthesis T. So, the Hartree-Fock energies will be same as the original one. So, I am not going to look at it. So, I will just look at the CCSD parenthesis T. So, you see there is a change in the 4 digit. Now, our triplet calculation is also done. This is what is showing. This problem sometime you can have. So, it is showing that the max core available is 0.6 is 392, whereas minimum memory needed is 699. So, sometime because in the open shell you have more number of variables. So, you need to store a more, because my alpha beta and alpha alpha will be different. So, I sometimes need more memory than the closed shell. So, in that case what you need to do, you need to give a max score here. So, I will write percentage max score and I give a memory of 1000 MB, that is 1 GB. My laptop has that kind of memory, but if you are using a laptop with less memory, then you would like to close all your browsers and all other things to actually perform the calculation. Okay, again an error. Okay, some problem with the guess file. So, a good idea will be to remove the GBW file. So, now it will no longer start from the old guess. So, when a big calculation runs, generally what happens is that it's your computer need to do more work. So, laptop gets heated up. So, you need to be careful so that your laptop is well ventilated. Generally you perform these calculations in a high performance computing clusters which has dedicated cooling mechanism, and they are generally kept at a very low temperature below 20 generally. So, there it is no longer a big problem, but if you are doing it in a laptop, you should be careful with the cooling. And you can see there are large files are getting generated, and that is why I told that to do this kind of calculation you need sufficient amount of RAM and sufficient amount of hard disk space which are available. They are still running. So, sometimes what happens, what you see as a temporary file is that when you run this calculation, many of the data need to be stored. They cannot be kept in the memory because they are so large. So, they need to be stored in the hard disk, and this is what these temporary files are generated. When I say that it will require a large amount of disk space, it is because of this temporary file. Once your calculation gets complete, of these temporary files, most of them will be get deleted. So, your final output file is actually very less, but because while runtime all these temporary files are getting generated, so you need a large amount of hard disk space to do this kind of calculations. Still not over. I think it is doing the iterations. I am actually tempted to see at what stage it is. ch2 DLPNO.out, that is the file I should open. Now I think it is done. I hope it has not crashed this time. And how I know that this has not crashed this time? If a program has run successfully, all this temporary file is supposed to get deleted. You will be left with gbw file, .uno file, unso file, lock file. The lock files actually contains the localized orbital. So, if you want to visualize them, you can open the lock file and see how the localized orbital look like and how localized are they. But if it run cleanly, all the .temp files will be deleted, and because there is no .temp file, so I know that it has run cleanly. So, now I can go to the end of the output file. This is the final single point energy. I have to make sure that I take the minus sign this time correctly. So, the energy, see again it is changing on the fourth digit. It is 9.66. So, you get almost the same energy what you got from the canonical calculation. Just to remind you one thing, the DLPNO methodology for the open shell system, what you did for the triplet is only available for restricted open shell, or if you are using unrestricted orbital, it will use QROs, that is quasi restricted orbital. You have read that for the open shell system, the alpha and beta orbitals are not orthogonalized. So, you need to use the so called QROs, and where they are orthonormalized, and that is what is done. It's actually used it's actually generates QROs after your calculations are done, and then it does the thing. Otherwise, if you can directly use restricted open shell and do the calculation without generating the QROs. So, these are my UHF calculations, and after my UHF calculation is done, you see here it generates the quasi restricted orbitals. And so, in normal cases the quasi restricted orbitals will not be used by default, but here you have to write you have to give a keyword for it, but here the quasi restricted orbitals will be generated by default, because if you want to do an DLPNO calculation on the top of the unrestricted orbital, it uses the QR orbital. You could have started with an restricted open shell orbital and that would have run the calculation, but because either you have to use restricted open shell or a QR arrow out of it, That means you cannot do this calculation on a broken symmetry reference. So, you cannot do a broken symmetry calculation and do a DLPNO-CCSD open shell calculation on the top of it. This is a limitation of this method. So, in this video you have known about various techniques to reduce the computation cost of calculation. You have known about approximations which approximate the Hamiltonian density fitting, chain of sphere or cos-x approximation. You have came to know about approximations which truncates the wave function, perturbational theory. DLPN actually uses a part of the perturbation theory to generate the natural orbitals and to select the pairs. Localized orbital for the occupied space, pair natural orbital for the virtual space, and now you believe you are ready to use the approximate methods, the arsenals used in the ORCA for your practical calculation. Thank you.